Right, I think I'm live. I hit start streaming, and hey, everybody, it's Tom Dimitrovich here. And coming to you for live for the IAEI News Live session. Today's topic, I see Lou Petrucci, and I got Jody Wages and Steve Terry out there. Give me that thumbs up. Put a chat in there. Make sure that we're golden. Today's discussion is going to be on the special purpose Gsci. I have Nehad El-Sherif waiting in the background for our discussion. And it basically, it all starts now. All right. Okay, everybody. I got Nehad El-Sherif. Nehad, welcome to IAEI News Live. How you doing, buddy?
I'm good, Tom. How are you doing? How's everyone doing? It's been a long time since last week. I missed IAEI Live.
Yeah, that's right. So we were live in Canada, in Ontario, Canada, talking about all kinds of stuff, right?
Yeah, I think we. In my opinion, I think we did a good job trying to cover what was happening in the industry, the TIAs and the CAMs, and then we touched on a few things. And your presentation at the Pulp and Paper, IEEE Pulp and Paper conference, and my presentation, and then we touched briefly on special purpose GFCIs. And this one, I guess we decided that hey, let's just have a session on special purpose GFCIs.
Yeah, and so before we get started, and I know we did a little bit of an introduction during our meetings last week, but just for those who are tuning in now, why don't you give everybody, all the viewers out there, Steve Froming with a special hello, and Lou and whatnot, give them all just a little bit of background, your background, who you are, and the code panels and stuff like that you're involved with. So take it away, Nehad.
For sure, yeah, I'll try to be brief. So my name is, actually, you guys know, Nehad El-Sherif. I live in Canada, been in Canada as Canadian citizen, been here for 16 years in Saskatoon, Saskatchewan. You look it up, you probably don't know where Saskatoon is. It's a nice area. Yes, Western Canada. Originally from Egypt. I was born in Cairo, and this was the reason I was joining Tom's channel a couple times from Cairo, because I was there looking after my mom. My background, I'm an electrical engineer. I have electrical engineer master's in protection, and almost got a PhD, but I didn't write my thesis, so I don't have a PhD. I have an MBA, and started my career as an R&D engineer in Littelfuse Starco. And this is kind of where it gets relevant to the discussion, because I was my first project I worked on the R&D was the special purpose GFCI. I was designing the first commercial special purpose GFCI Class C and Class D. It was a team effort. It wasn't my design, but it was my project. I was kind of responsible for. And I worked from the design. I still remember it was just an idea on a sketch on a piece of paper, and I was lucky to take the idea all the way through the process until we got to UL certification, and we had a product at the time. Then I moved to product management, and one of my responsibilities at the time was to promote this new technology and how it relates to safety. Just kind of more like educating the industry about this new technology that has been made available by Littelfuse Starco at the time. And I guess this is the time when I became more involved with the electric safety workshop, PCIC, Pulp and Paper, IEEE conferences, and NEC, and UL, and all those other interesting standards. That's how I met Tom at the very beginning. I don't work for Littelfuse anymore. Now I'm just kind of doing my own consulting stuff on my own. And I have the honor to sit on panel 2 with Tom, representing IEEE, and I'm a member of the STP Standard Technical panel for UL 943, which is the standard for GFCIs in the US, and I serve on the equivalent panel for the Canadian CSA standard. Both of them are harmonized, anyways. I serve on 1699, which is the UL 1699 AFCI standard, UL 943 in the US. and I also serve on a few other committees, Z462, which is the 7E equivalent in Canada. So I am an associate member, which means I don't vote on the Z462, but I'm a member of the committee, of the standard committee. And yeah, I guess I don't want to bore people with what I do, but I've been heavily involved with the safety, and it's actually a pleasure. Like Tom would probably attest to this. It's once you start, it's just an addiction, and you can't let go. It's you make friends and relationships, and I would highly recommend it for anyone who is considering to become part of the code and standard development process. It's very rewarding.
Excellent. And we got Doug Kerr out there on LinkedIn. We're saying welcome to Doug. And we got, Shokri, I guess, and a few others coming in on LinkedIn as well as YouTube. So thanks everybody for joining. And thank you, Nehad. I know you are a valued member of a few committees that I know I'm engaged with, and Code Making Panel 2 is one of them. So although anything we talk about today is not in, it is not, we're not speaking for Panel 2, we're not speaking for NFPA, or I'm not speaking for NEMA, you're not speaking on behalf of IEEE. We are two individuals having a discussion about this thing we call Gfcis, right?
Yeah, it's our personal opinion, so nothing would be, nothing should be taken as representing any of those organizations. It's just Tom and I having a discussion, hopefully sharing our opinions with everyone tuning in, and hopefully it's a two-way conversation. Like I see some comments on YouTube. Jody Wager said he tuned in today because he wants to find what his special purpose is for. So I'm not sure how can I respond to this, Tom.
I don't know, but I'll tell you what, we're going to help everybody understand what a special purpose Gfci is. So the first thing
Panel 2 as well. So hi, Jody.
Yeah, hey, yeah, that's right. Jody is also, he represents IAEI on Code Making Panel 2. So let's first talk about the definition of a Gfci. So Nehad, I know this can be confusing for some people. In fact, I have sometimes have a hard time with some individuals. They'll just say, I need GFI protection. And you don't know if they're talking ground fault circuit interrupters. I don't know if they're talking ground fault protection of equipment. And now we've got a special purpose Gfci. So I think covering the definition of what a Gfci is and establishing that as a baseline is probably a good thing. So this is the definition out of the NEC. So you want to speak to just the concept of a Gfci?
Yeah. So this is the definition of a special purpose, right? And this definition is supposed to be appearing in the 2023.
No. This is Gfcis. So this is the 4 to 6 milliamp. So this is what is a Gfci, ground fault circuit interrupter, which is your Class A device, right? And
yeah, I didn't read. I thought it was you talk about special purpose. So now I'm reading the screen. So I guess I think it helped our viewers to take a step back and forget about the SPGFCI, GFCIs, EGFBD. All the acronyms are very or GFPE. All the acronyms are confusing. So let's just kind of talk about the basics of the whole idea. At the end of the day, all those devices are ground fault protection, right? And what's a ground fault protection? I guess to go back to the very basics. So electric circuits, we design circuits so we have a circuit, so we have the current should go through conductors and then to the load and then back through the neutral or the return conductor to the source, right? So this is a well-designed circuit, no problems whatsoever. The current is going through a conductor and to the load, back to the source through another conductor, whether it's a neutral or another conductor, let's say the another phase, or if you're doing three-phase, or the center tap kind of application for transformers. The problem arises when there is, just like Tom is showing the screen on the screen here, we have an alternative path for current. And remember, electrons are smart and they will take every path available to go back to the source that they originated from. It doesn't matter what the impedance is, because I mean it's a common mistake to think that electrons will take the path of least resistance. This is not true. They will take any path, but more electrons would go to the path of least resistance for sure. So maybe 90%, 95% of your electrons would go through the path of least resistance, but then you have this 5%, maybe 2%, whatever the percentage is, depending on the impedance, the ratio of the impedance, that will be going through the alternative path to get to the source. And this is where the problem is. Like just image that Tom is showing, if there is a path through ground, which what we call refer to ground, the equipment ground, the conductor connect to ground, and just like through ground or the ground mat or whatever back to the source, the electrons could take the source. The problem is if someone comes in contact with a faulty equipment because of this extra path to ground, then just like the image is showing, the current can take the path back to the source and the ground through the person's body. So now you can think of this person as another impedance connected to the source. So yes, most of the electrons would go through the normal path. I guess the screen is showing the 10.9 point something. I can't read; it's just too small. But yeah, I guess it's just only 5 milliamp or something, very small, 0.005. Yeah, thank you, Tom. Yeah, so you have 10 amperes going one way. Yeah, this is my image, but I forgot the number. So 10 amperes going one way, but then the return is only 9.955. The difference is 5 milliamp, 0.005 amperes. This amount is returning to the source through a different path, which happens to be this person, which could be a shock hazard. So at the end of the day, and this applies to people and equipment. So at the end of the day, it's a ground fault that we're trying to protect from.
Mm-hmm.
But because the tolerance of human is much less than machines, like if you have a motor or a pump or any piece of equipment, equipment can tolerate much higher values of ground fault going through them without starting a fire, without having a failure or problem, right? So we have to split the idea of ground fault protection into two, I guess, categories. We have personal protection, which is it's protection at a lower current value because of our heart, and we'll get into fibrillation, I guess, shortly and the details, the impact of current on humans. But we split this into human personal protection, which is dedicated for human. Same theory of operation as equipment protection, but equipment protection does the same job, but at a higher threshold because, again, equipment are more tolerant to current than humans.
Well,
So
yeah,
now
and so you from an equipment protection for everybody's benefit out there, 23095 in the National Electrical Code sets a maximum threshold of 1200 amps for ground fault protection of equipment. In addition, you'll see GFPE over in Marina's in Article 555 at 100 milliamps, and now we reference 30 milliamps as well. So there are the main, I would guess, when you think of ground fault protection of equipment, you're thinking about amps. When you think about Gfci, you're thinking about milliamps. So it's big amps versus little amps.
Like you said, so the 30 milliamp even allowed in Marina is still dangerous for humans. That's why we can use the 30 milliamp for personal protection. But the other thing I would urge people to think about when you think about personal protection is amps, for sure, milliamps, and time, because time is critical.
Yes.
For a machine. Like Tom mentioned, 230.90, right? 230.90. It requires tripping within 1 second, right? And this is a lot of time for people. Like this will be enough to kill a person. Like there's just no way that a person can tolerate any current, even if it's a small amount of current going through their body more than 1 second. This is a lot of time. So that's why we mainly think about the amount of current, which in our case in personal protection be milliamps, and time is a crucial as well. I guess time is important in both arenas, personal protection and equipment protection. But of course, for personnel, it's becomes more critical to make sure that we trip within allowed time that would not cause any damage, internal damage for organs, and physiological damage, which we'll be covering shortly, like the effect of current. But just I would want people to think time and current, not just current. Time is very important as well, because at the end of the day, it's energy, right? And then I guess if we talk about personal protection, now we have two groups under the personal protection umbrella. We have Class A Gfcis, which I believe everyone is familiar with. It's the kind of protection that has been installed in homes and commercial applications since, I guess, the 70s. The first NEC requirement for Gfcis were kind of in the 70s, right? So this is Class A. Now we have a new, I guess, member of the personal protection family, which what UL refers to as special purpose Gfcis, SPGFCI. And SPGFCI is, I just want to emphasize that because the name special purpose doesn't imply that they are used for special applications or special purpose applications. They can be used in any application that Class A can be used, but then there's different requirements and details. So you can replace special purpose GFCIs and use them instead of Class A. But I mean, the application itself, they're not special. They can be used in any application that require personal protection, but there will be some requirements that we'll be covering shortly here. Tom and I will be covering, but just as a general idea, we have ground fault protection, personal protection, equipment protection. And under personal protection, we have Class A and we have special purpose.
Yep. And so if you look at this definition, anytime you see the word ground fault circuit interrupter, if it is a ground fault circuit interrupter, then it falls back on this definition, which tells you that it functions to de-energize that circuit with an established period of time, which is what you just spoke to, when it exceeds the values established by a Class A device. And we're going to understand the difference between a Class A, C, D, and E, and we'll throw B in there for a discussion as well. But UL 943 is the standard, and what it says here is a Class A ground fault circuit interrupter trips when the ground fault current is 6 milliamps or higher and does not trip when the ground fault current is less than 4 milliamps. That's why a lot of people will say 4 to 6 milliamp device or a 6 milliamp device, but that's where that comes from. So that's the definition of.
Some people would refer to Class A as a 5 plus minus 1. So
Yeah.
5 milliamp minus
Sure.
1. So
Yep.
It's all the same. Yeah, you trip when it's 6 or higher. You don't trip when it's 4 or less.
Yep. Okay, so that's your GFCI. So now let's move over to talk about this is a new definition that was proposed and has been accepted for the 2023 code cycle. This is the special purpose GFCI. Now, the definition says that it's intended to detect a ground fault currents used in circuits at a voltage to ground greater than 150 volts, and it functions to de-energize a circuit. So this wouldn't be, you wouldn't find this since it's a voltage greater than 150 volts to ground. So that would not be a 120 volt single phase circuit, right?
And this is the first difference, that when I said that, they're application wise, they can be all used. Any application for a Class A can be used for a special purpose, but when you get into the details like voltage, at homes, for example, you can use a Class C or Class D because it's not 120 volt. I mean, what we use at home is 120 to ground. This is 150 or higher. So this is kind of the first distinction between the two, that we have higher voltage to ground tolerance for these GFCIs, for the special purpose GFCIs Class C, D, and E compared to the Class A. And I guess this is not the colloquially and internally within Littelfuse, when I was still working for Littelfuse Starco, we call those new classes of GFCIs industrial GFCI.
Right.
And the reason is that it's more geared toward industrial applications, maybe commercial applications, where you're protecting individuals who are not kids and women who be like at home. You just want to make sure that you have more. You're less tolerant to ground faults. This is more, if you're like at an industrial facility, you're expecting more qualified people. Of course, you still have to protect them, but that's why this would justify the reason for the increased threshold for tripping that we'll be covering right away.
Right.
So I guess 150 volt to ground is a key, and the differentiation between the two, the special purpose and Class A. I guess we have to use classes now because we can't say GFCIs anymore. That's Class A GFCI and then special purpose for Class C, D, and E.
Yep.
The other thing I'd like to point out here in the definition, Tom, is the standard that governs these new classes of GFCIs is called UL 943C. And this is not to be confused. The C is not to be confused with the Class C. It's just simply the UL 943A or UL 943 is Class A GFCI standard. And then there's UL 943B, which is the appliance leakage circuit interrupters, another class of equipment that's used for protecting appliances like hair dryers and I guess hair dryers is one thing I could think of, and those kind of equipment. And then the third member of the family of 943, which happened to be 943C, is the outline of investigation for special purpose GFCIs. An outline investigation, again, it's just it's not that it's inferior to a standard. The difference between a standard and an outline of investigation from a UL perspective is that the outline of investigation is a document that has not gone through the ANSI process
Right.
to qualify to a standard, but but the requirement is still valid and it can be used for certifying products, and it's just as safe as a standard. It's just a matter of paperwork, and my understanding UL has a long list of outlier investigations. It's a matter of when the document goes to the ANSI process first, because of which documents are in more demand.
So Don Ganir said he had a concern about that, and my answer to that, Don, is if you just look through the code. I just did a search in the 2020 code. There are UL Subject 2755 outline of investigation for modular data centers, UL 497E outline investigation for protectors of antenna lead-in conductors, 1724 outline investigation for fire tests of electric circuit protective, and 805. So there are many sections, there are many references to products that are listed to an outline investigation, and that's the journey of a product to a standard. So I'm not as much concerned about that. In fact, I appreciate it even more because there are many cases where a product is not even required to be listed. At least these products are getting third-party review. So that's where my head's at on it, but everybody has a different opinion. Obviously, in Don Ganir's, and hold on, Nehad, in Don Ganir's, mind, he has a little concern about that, and that's fine. Everybody has a thought process in that regard. So just be mindful of what that is. That's all.
Yeah, and to Don's point, I was going to add to what you're saying, Tom, that it's because it's an outline investigation doesn't mean that it didn't go through the consensus process.
Yeah.
Because when UL has a draft, so there's a difference between a draft and outline investigation. A draft is something that was drafted by maybe industry or at UL and hasn't been shared with the industry yet. But for the outline investigation, it's like an extra step after a draft. So draft standards, just something that was just drafted, no consensus. This was supposedly shared by industry, and no one had any, immediate issues with the draft. So the draft became an outline investigation.
Yep. All right. So
next step in the process is to make it a standard by doing the paperwork required by ANSI, like an ANSI standard.
Yep. So there was another question came up from Mervin Savanstianik. Hopefully I got that right. He made a statement. I'm sorry?
I know Merv. Yeah, Merv is a friend of mine. Hi, Merv, from Saskatoon.
Excellent. So another comment from Saskatoon. He says that the Canadian Electrical Code has separate definitions for Gfci and a Class A Gfci. And to add to the confusion, what's that all about? I mean, do they have a definition of what a Gfci is and then another one for Class A? Are you aware of that, Nehad?
I believe it's a non-Class A because in Canada, so again, UL 943 is a harmonized standard. So Class A is the same definition in Canada, US, Mexico. It's like a North American standard.
Okay.
This was harmonized. UL 943C, Class A, C, D, and E, it's only a US standard. So this is only defined, like those classes are only defined in the US. Canada and Mexico are not using the same standard, but in Canada, pre the harmonization of Class A, there was an old standard, which I don't remember the number, but I can get it for whoever interested. It's M91-something. I have it somewhere.
Okay.
This standard was defined what they call Class A and non-Class A Gfcis. So non-Class A Gfcis are those Gfcis that can go up to 600 volt voltage, line-to-line voltage, which is kind of similar to Class C, D, and E, but they're not called C, D, and E in Canada. They're just like non-Class A Gfcis.
Okay.
Like anything that doesn't fit under the Class A umbrella pretty much in Canada is non-Class A Gfcis. I think that's what Merv is referring to, but please correct me if I'm wrong, Merv. But probably this is what my guess is.
Excellent. And Don Ganir had another question. Is an outline of investigation reviewed by the various stakeholders that are required for a STP to issue a standard? And I know, Don, that various outline investigations, what UL will typically do is go out to get eyes on it from different perspectives. So does it go through a formal STP process? No, but there are more than just one person looking at this, and there's more than just one manufacturer looking at some of these. They do get, I don't know if you call it a peer review of some sort, but UL does have a process to solicit information from other sources. And you know what, this might be a great discussion, Nehad, because we're almost at the bottom of the hour. But I think I might try to reach out to UL and see if we can't get a representative on here to do a program just on what an outline of investigation is, because it's used many times in the National Electrical Code. I mean, I have 8 full pages. I searched outline of investigation in the 2020 code, and there are 8 pages on NFPA link of reference sections that reference outlines of investigation. So, Dawn, stay tuned, brother, because we're going to have probably another program in the future, and we'll cover that topic. So, cool.
This is a good point, Tom. I think it would be a good idea for a program. And yeah, to your point, I agree. This is not the first time an outline of investigation is referred in the NEC. The National Electrical Code has many instances of outline investigation. So,
all right. So let's talk about the shock and protection. So we know the resistance of the body, right? And we get that information. I don't know, Nehad, and I've shared some of that information with you, but I go back to the 30s when testing was done on when a manufacturer wanted to come out with a product to provide a fence, an electric fence around that we would use on farms, because farmers back in the 30s were taking electricity, running it around an area and to keep cattle in, and unfortunately children were getting killed. So a manufacturer came out with an idea to create pulsed DC to shock the cattle but not kill you. But then UL was like, wait a second, how do we know how much current can kill you? So they did research, and that was even before Dalziel. Dalziel didn't do his research till what, like the 60s and 70s?
I think, yeah, it's 50s, 60s, yeah.
Yeah, somewhere 50s and 60s, somewhere in that ballpark. So this was the 30s, 20 years before him. UL had done some research for this electric shock as it pertains to fences. And I know a lot of these resistance values that we see here, the finger touch, dry and wet, finger to thumb grasp, all what they're trying to do here is establish the fact that when your skin gets wet, you have a lower impedance, a lower resistance value, which can, again, it's all about circuits. And then the chart to the right, again, taken off of research that was done by UL and Dalziel and probably others, to talk about when does the heart go into fibrillation, when does our muscles start to contract, and trying to determine the whole concept of the differences between what a let-go threshold is and then what a defibrillation threshold is. You have those two, I would say, Nehad, those are 2 key points, data points in the whole, I don't know if you would call it a philosophy or if you would call it a strategy for safety. It's at what value of current do I want to make sure that I open a device quickly? Is it to prevent the person from not being able to let go, or is it to prevent the defibrillation? And I think that's 2 philosophies. One that we have here in the United States is a little different than what you see over in European countries, right?
Yeah, absolutely, Tom. This is the exact difference between Gfcis in North America and RCD, residual current devices, in Europe. And this is exactly what they did in Europe. They only provide personal protection for ventricular fibrillation, like Tom was saying. In North America, we provide both ventricular fibrillation and leg go protection. That's why the limits are a little bit lower in North America. Yeah.
And I love this slide. And I know you and we did a IEEE paper, and this chart, it came out of that. I believe you put a lot of energy into this one. Why don't you walk people through what are we looking at here?
Sure. So this slide is taken from an IEC standard 6479-1, the physiological effect of AC current on living stocks. I believe the title of the standard is. And what they did simply, they went with the x-axis, or the horizontal is the current going through a person's body in milliamperes, and then the vertical axis is the duration of current. And they just came again, just to be very clear, this is all probabilistic. So this would be the case of a healthy individual, which would be the I think the 90% percentile of population, like dry skin and no heart issues whatsoever. Because all those conditions would impact the effect that would lower the amount of current that would be needed to cause the same damage that would be implied on a healthy person. So they kind of went through this research, and I guess it just at the very first, the green area is more the area of inception. Like anything under zero point 0.5 milliamperes, you probably would hardly maybe feel it, but it just doesn't have any harm on you. And then when you go again, then this is, I'm just talking about the amount of current, but then this time as well. So don't forget the vertical axis. And then when you get to the I guess orange or dark, yeah, I guess orange color is. I'm not good with colors.
Yeah, right
The
in
orange
here.
color, yeah, this is the area that there is no permanent harm. But if you notice that the area is, the more time, the skinnier, the slimmer the area becomes. Like the line, the dotted line is inclined at an angle. So if you are at a low current, let's say 5 milliamp, you can go all the way up uh, to a much higher current, much higher time, without really moving into the following area, which is the red area, the light red area. And if you at, let's say at 30 milliamp, you need less time to transition from the dark orange area, with the orange area, into the light red area, kind of thing. So again, it's time and current. So as long as we're in this area, the no permanent harm area, this is kind of where GFCIs try to operate. With, yes, you would feel the zap, you'll feel that there was a shock. I'm not saying that it's not like the green area that you barely feel anything. You still feel that the current, but it's just going this area. If the current is interrupted, either by a person letting go of the circuit, or interrupted by a device, GFCI in this case, then there will be no permanent harm occurring.
So in this, like I can't help but recognize the 5 milliamps lines up with this B line right up here, right?
Right.
So what we're saying is that any current, these currents that are less than that 5 milliamps, that is you have no permanent harm. And is that your let go threshold? That's where you will be able to let go if you're less than 5 milliamps?
For sure, and this is the GFCI class A GFCI threshold, right? And it was designed because usually the let go, again, the 90% percentile of people and healthy, dry skin and so forth, is around 8 to 10 milliamp. So I guess like 8 is maybe for kids and women, and goes up to 10 for adult male. So 5 is much lower than this limit, which means that you'll be no permanent harm. You can let go your circuit. You don't need a GFCI to interrupt power for you. That's why Tom and I initially said that Class A GFCIs provide both let go and ventricular fibrillation.
Okay.
Because yes, at that point you still can let go, but the device would interrupt power maybe quicker than you let go. So it's still providing these two kinds of protection. But if you move higher up, and this is where it gets interesting with the special purpose GFCIs, up to 20 milliamp or 30 milliamp in this area, then time becomes really crucial. Because if you don't trip quick enough, then you can get into the red zone, which is the muscle contraction. Like pretty much like you lose control over your muscles. You won't be able to let go anymore, because the amount of current is high enough to prevent muscle control.
So in other words, like at around 10 milliamps, if at 10 milliamps, you have milliseconds, so you have 2,000 milliseconds. So that 10 milliamps can flow through your body for up to 10 milliseconds. After the 10 milliseconds, now you're getting to a point where you have involuntary muscle contractions. But nobody has that full control of being able to let go that fast, right? So that's why that 5 milliamp line is where we operate. Anything above that, we're operating. We want to make sure that we remove the current passing through your body fast, so that you don't end up into that involuntary muscle contraction perspective. So That's where.
Tom, I think you said 10 millisecond, but it's much higher than this. Probably 100 milliseconds or something, or so.
Well, I'm just
Maybe
looking at the chart. So it's 10 milliamps,
right.
and if I move it, come all the way up to this dash line and go over, it's 2,000 milliseconds.
It's like 2 seconds. Yeah.
Yeah, 2 seconds. So
Yeah.
so what we end up doing is, from a GFCI perspective, the goal of the GFCI is to remove that current flow passing through the body so that you don't have to be consciously thinking about it to say, I feel this, I'm going to remove it. And I only got 2 seconds to do it. But if it's at 20 milliamps, you'll have, I don't know, maybe 500 milliseconds, right? And if it's 50 milliamps, then you have maybe a little less than 200 milliseconds. So the higher the current, the shorter amount of time it takes for you to move that from your body reacting such that your muscles are contracting and you can't let go of whatever it is that you're touching.
Because I guess the bottom line is our goal is to prevent getting into the red area. And of course, the light red and then the dark red. The dark red is much worse than the light red. But this is kind of our goal, to make sure that we don't transition into that area when it's, just becomes very dangerous. And like Tom said, you be involuntary muscle contraction. This is very similar to what happens when you do the, in the electric shock drowning, right? When people just sink, just drown because they can't control their muscles anymore, which is, unfortunate. Just because of the amount of current going through their body, just too high, and they can't swim anymore.
Okay, and then to your point, the higher the current you go into, now you're moving into ventricular fibrillation, and now that you're getting that heart losing its beat, so to speak, because you're at that 60 hertz frequency, et cetera. And now and again, it's a equation of current and time. So say 200 milliamps for, say, somewhere around a little over 500 milliseconds, you're moving in, you're going to have involuntary muscle contractions right off the bat, right? And then the longer that current passes through the body, you'll get to a point where your heart will go into fibrillation, ventricular fibrillation.
Exactly. And I guess Duncan here had an interesting question that we're going to answer in maybe a minute. His question is, does the special purpose GFCis have the same formula for maximum time to trip as a Class A Gfcis? And I would say absolutely. And Tom and I were going to discuss this once we kind of finished this slide, which I think we're pretty much done. We are.
So what I want to do before we move on, though, I want to remind everybody that you can order the analysis of changes right now. We're in pre-order status. You can go out to the IAEI.org's website. I put the link in the chat earlier. Also, I am informed by my buddy, and Michael Hofkin's already working on getting a person for the program. My buddy Jody Wages says, if I have the opportunity, please let folks know that the IAEI has their 2017 NEC-based training book available for free. So I want to remind you of the 2023 code changes book, but if you want the 2017 based training book available, it can be free, and you would just have to pay shipping. But reach out to Jody Wages, Joseph Wages, and his Jody. If you're out there, put your email in there. If not, reach out to me. Send a note to IAEInewslive@gmail.com, or send it to Jody Wages. If you can go out to the IAEI's website and send a note there. So that's that is awesome. So if you're on the 2017 NEC, you've got some free materials coming from the IAEI. So please jump on that one. And hopefully when you do that, you are a member of the IAEI. All right. So where do you want to go next, Nehad?
I'm not sure what's the next slide, but I guess
you want to go to the three-phase? We already talked about the single phase. This is the three-phase example of current flowing through the body. I don't know. I think your point here, regardless of whether it's a three-phase or single phase, the point is Currents will take all paths back to the source. I don't care if it's a good, you could have a grounded system, you can have very well bonding going on. That's not going to stop current from passing through your body. You have an energized enclosure, whatever that load is. If it doesn't clear that overcurrent protective device and it stays energized because the current values are low enough, then it can pass through your body. Now, and the next slide is your classes.
So the point from the previous slide is to emphasize that class C, D, and E are three-phase. You can get a three-phase and a single-phase class C, D, and E. Class A Gfcis is only a single phase, but in terms of the theory of operation, it's very much the same. You have all the currents going through a current transformer, like a zero sequence current transformer, or the donut, we call it. And if there's any differential of the current going to the load is not exactly the same amount going back to the load, then the device would detect this difference and would trip in a time proportional to the amount of difference or the leakage current that is happening, which we'll be showing this in a couple slides to answer Don Ganier's question as well.
Excellent. Excellent. And Michael Hofkin said he just put Jody Wage's email in the chat. So excellent. All right. And Jody says that this offer is for all of our 2017 based books that they produced. That's the analysis. Oh my gosh. The SOARS, photovoltaics, 1 and 2 family, study guides. It doesn't include the 2017 National Electrical Code, so be mindful of that. We can't give away NECs because we pay for those. But anyway, that's a great piece of information. So perfect. All right. So, do you want to talk about the next slide?
For sure. If you're ready.
Let's do it.
All right. I guess this is kind of where hopefully we are able to clear the misconception or misunderstanding or the confusion between the different classes. And it just starts with the voltage to ground. And this is an adoption of, this chart is adopted from UL 943C standard, or outline of investigation, not a standard, outline of investigation, which defines class C, D, and E. And this is where I guess the definition or you can figure out in your application whether your application requires a class A, class C, class D, or class E. It all starts with the voltage to ground. And like the definition said, if the voltage to ground is over than 150 volts, then you're getting into the special purpose area, the class C, D, and E. The only exception is if you are using double insulated equipment or equipment grounding is required, which is something that you don't see at home. Like you don't have an equipment grounding conductor for your toaster, for example, or dryer, right? So this is kind of class A area. But if you have those requirements and your voltage is less than voltage to ground is less than 150, and you require equipment grounding, then there would be a class C is your go-to. Like if you follow the no to the left and then yes for the equipment grounding, insulation, and double insulation requirement. But let's just go to the right-hand side of the chart, which is over 150 volts. This is where it gets into the special purpose area. There's no class A that would meet this requirement. Like the maximum voltage line-to-line voltage for a class A is 240 volts, so it doesn't meet the more than 150 to ground requirement. So if you have 300 volt, over 300 volt to ground, this would be C and D. But then if you have less than 300 volt to ground, this will be class C, which is simply the let's say the 2.8 applications. Anything that like your voltage to ground is less than 300 volt. The interesting thing is when you have an application that is over 300 volt to ground. I guess 480 volt as well, class C, you can get class C 480 volt applications because the line to ground for a 480 volt system is less than 300 volts. Becomes interesting, and this is kind of applies more on the 600 volt systems, which is mainly in Canada more than US. US is 480 volt distribution voltage, so you'd be pretty safe using class C most of the time. But when you get to a voltage to ground higher than 300 volt, UL has a distinction between a class C and a class D. The distinction is if your equipment grounding is oversized, equipment grounding conductor is oversized, and there's an equation in Appendix A, I believe, in the UL 943C that kind of shows you how to oversize your grounding. And if you're the point is they oversized the grounding to limit the voltage to ground to 150 volts, which is kind of considered, relatively safer voltage to limit the current going to a person, because the current going through a person would eventually be the voltage to ground divided by the impedance of that person. So 150 volts divided by the impedance, which is roughly, to talk about, like UL uses 500 ohms for the like a typical value. It's like 500 to 1.5K, but use 500 to be safer. To kind of do the math, and this is the amount of current leakage that you'll be allowing to go through the person coming in touch with a faulty piece of equipment. But if the equipment grounding conductor is not oversized, which is probably the case for, I would say, 99% of the facilities, then or establishment we have, then you'd need to use a Class E. Class E is what UL refers to as the ultra fast tripping, because it trips much faster than Class D. So you don't oversize your grounding, but you trip much, much faster than Class D. The bad news is Class E does not exist as we speak, because you can achieve those requirements, the new equation that Class E has when you go over 250 milliamp. It just you can't obtain the strip time with a mechanical device. Like you can have a mechanical device like a breaker or any mechanical contacts to trip that fast. So Class E, as we speak, does not exist. The only special purpose GFCIs that commercially exist are Class C and Class D. Again, excellent. For our US viewers, Class D is mainly for 600 volt line-to-line 600 volt systems, so it shouldn't be a concern. Most likely you'll be using a Class C. D is more, on those very limited systems, mainly in Canada and very limited in the US, that you have 600 volt system.
Excellent. So here in the United States, with regard to now we're going to get into okay. So Fred B says, what difference is there in a Marina grade GFCI? So if you're saying, Fred, if you say GFCI, you're talking about a ground fault circuit interrupter. You're talking about a Class A device, which has that 4 to 6 milliamp trip time. And from a Marina grade, I don't know that there's any special category. I mean, you would probably want something that's weather resistant. It would have to be in a certain from an enclosure and an environmental perspective. But now there are ground fault protection of equipment in marinas. There's an Article 555 has requirements for 30 milliamps, but that's GFPE. That's not GFCI. That's ground fault protection of equipment at 30 milliamp pickup. And the clearing times, they don't use the same equations that you have for GFCI. All we're worried about in using the 30 milliamp or the 100 milliamp ground fault protection of equipment in marinas is to detect a problem in the circuit. And then now, Nehad, I know it's 12:47, so we got 15 minutes. We still got to get through Article 680 code requirements. So
quickly to Fred's point, I believe Marina grade GFCI is a marketing term. I haven't seen it before, but it sounds like a marketing term. From a standard standpoint that Tom and I are discussing today, there's no such thing as Marina grade GFCI. It's Class A, C, D, or E. This is kind of what UL defines and what the NEC is defining. So it's probably just a marketing term. Back to the slide, I guess we're kind of running out of time. The slide here, this is kind of to answer Don Guinier's question. Yes, Class C, A, C, and D use the same equation. Effectively, what we did is we moved the starting point of the tripping curve, and instead of starting this equation, that 20 divided by R to the power of 1.43 at 6 milliamp for Class A, you kind of moved it to the right a little bit. So now we start for Class C and D at 20 milliamp instead of 6. The Class E that I mentioned is not shown here, but a Class E that I mentioned, like if you notice, the curve kind of gets to a point that it just becomes like a definite time, so that the curve is horizontal, which means around 300 milliamperes, you are not required to trip quicker more than 20 milliseconds. This is kind of the quickest time that you are required to trip at for Class C, D, and Class A, right? The difference with Class E, when you get to 300 milliamp, you move to another equation. I think, if I remember correctly, it's 6 divided by I to the power 1.43, which makes another inverse time curve, makes it much, much quicker. And this is what I was referring to.
And what's that one on? What's that one on? You said that when you get to, is that a Class E?
Class E. When you get to the 300
Okay.
milliamp for Class E, you don't have the fixed time anymore.
Okay, but Class E's don't exist.
Right, and this is the reason it doesn't exist, because the new equation is much, much quicker. That I think you're required to trip within 6 milliseconds or something,
I
which
gotcha.
makes it impossible for a mechanical device to do this.
Gotcha.
In
So
the future, I'm sure there'll be technology that could meet this, but as we speak today, Class E does not exist for this reason.
okay, so when we were talking about this earlier slide, remember, you're saying that the Class C and D devices pick up at 20 milliamps right here.
Right.
And they follow the same equation for trip times as a Class A GFCI, but you just increased the threshold.
Yeah. You're delaying your starting point, pretty much. Like instead of starting at 6, you're starting at 20.
Okay, so the vulnerability really is right in here where you could have a current, and this would be if the current is less than 20 milliamps, but greater than approximately 5 milliamps. If the circuit is such that that's how much current is flowing based upon you touching it, and the impedance of the conductor and all that other good stuff limits that current to less than 20 milliamps, but greater than 5 milliamps, a difference of about 15 milliamps, right? That window of 15 milliamp window is what you're looking at with regard to you could possibly have involuntary muscle contraction. Your heart's not going to go into defib. But to Robert from Omaha's point, he said, you can't forget the fact that you're cooking somebody from the inside. But hopefully someone is there to push you off or you fall off. But in any case, that's the window that you're missing. So that
exactly.
Yeah, that
and I guess, Tom, when you have a 20 milliamp or higher ground fault, and technically it's 15 to 20. Remember when we said Class A 4 to 6, Class C and D are 15 to 20. So anywhere between 15 to 20, we just use 20. We use the 6 for the threshold. But when you have a 20 milliamp or higher ground fault and you install Class A, Class C, Class D, all of them will trip at the same time if they are certified or listed and meet your requirements, because it's the same equation. Like Tom said, the only difference is if you have any ground fault between 6 and 20, then Class A would trip, but Class C, D will not trip. And in the standard, UL gives an option for manufacturers to design a Class C that can go lower than the 15 milliamp that you can trip, maybe at the 6 milliamp as well, like only Class C. But the issue is, those devices, like I mentioned, were mainly designed or introduced for industrial applications when you have more leakage current due to humidity and long cables and so forth. So if you go down to 6 milliamp, it kind of defeats the idea of having higher leakage current, because at homes we don't expect to have high leakage current, but at industrial applications facilities there will be expected more leakage current. But I need to emphasize something. The UL, which is something I don't think we're covering here on the slides, I'll just kind of talk about it quickly. The idea of UL to increase the trip level from 6 milliamp 5 plus minus 1 to 20 is under the assumption that we have reliable grounding. So remember the equipment grounding conductor, you only do this when you have what you refer to as reliable grounding, which means you have an equipment grounding conductor. We don't have this for Class A. Class A, you're not required to have an equipment grounding conductor connected to the appliance that you're protecting or the piece of equipment you're protecting. So what this means, reliable grounding, is the special purpose GFCIs have an extra layer of protection, and this requires Class C, D, and E to make sure that they are monitoring your equipment grounding conductor or the grounding connection of your appliance or your equipment that I guess I shouldn't say appliance, your equipment that you're protecting. And if there's a problem in your grounding circuit, aka your equipment grounding conductor is severed, not connected, the impedance is much higher than expected for whatever reason, the special purpose GFCI is required to trip. So it doesn't only trip because of the leakage current, it's now required to trip because if there is any grounding problem.
Because, and I just want to make sure that's an important piece. And what you're doing, and just help me describe this, but you want to make sure that the voltage across the body doesn't exceed a certain value, right?
Right.
What's that?
150 volts.
150 volts. So we don't want the body, the human body, whoever's connected from line to ground, to have a voltage greater than 150 volts. So what you're doing in this special purpose GFCI is you're monitoring that that equipment ground, that grounding and that ground connection, so that you limit that voltage. And if it's not there, then you can trip. So if for example you break, so if this is the special purpose, if you break this connection, it could trip just because you no longer have that equipment ground.
Sure, because think of it this way, Tom, and this is a great example. The 150 is the voltage responsible for driving current to the person. Just think of it as a circuit, right? You have 150 volt, and then you have the person's impedance. So the current going through this, the person's body would be dependent on the 150 volt, right? And the impedance of the person. The equipment grounded conductor role is, don't forget, it will be connected from the equipment to the ground, which is in parallel to the person, right? So just think, I know it's not on the image there, on the figure that Tom is showing, but just think of how equipment ground and conductors are connected. They're connected from the non-conductive metal parts of the equipment, like the chassis and everything that's not supposed to carry, all the metal parts not supposed to be current carrying, and it goes all the way to ground. So this equipment ground and conductor will be in parallel to the person, right? And based on the current divider, Kirchhoff current divider law, the higher impedance will get less current. So we're trying to make sure that the equipment grounded conductor has less impedance, so that most of the current driven by the 150 volt to ground will actually take the path of the equipment grounded conductor and not the person.
Gotcha.
Because if there's a problem in the equipment grounded conductor, if let's say we have a condition that the impedance of the equipment grounded conductor is exactly the same as the person, then the current will be split in half. Right? If the person has less impedance, the body impedance is less than the equipment grounded conductor, then more current would go to the person than the equipment grounded conductor, which is not what we want. So the idea for the special purpose GFCIs to monitor equipment grounded conductor is to make sure that we don't get into a condition that the majority of the ground current will go to the person. We need all the current, ideally, preferably all the current would go through the equipment grounded conductor back to the source. But in those cases that, it's a current divider circuit. You have two impedances, the person in touch with the piece of faulty equipment and the equipment grounded conductor of that equipment. So we need to make sure that the equipment grounded conductor impedance is low enough as designed to make sure that the majority of this current would go through that current bypasses the person and goes to the equipment grounded conductor back to the source, so protecting the person. That's why it's very important to add this piece. The special purpose GFCIs are required to not just monitor the leakage current, like Class A, they have an extra protection, extra requirement, which is monitor the equipment grounding conductor or your grounding connection to make sure that it's still sound.
Perfect. That's perfect. That was a very important detail to cover. Now, I want to take a look at the code requirement. In 680.5, I think there might be a problem with language. So let's take a look at this. 680.5b, Nehad.
I can only add to your library if you have an Apple Music subscription.
Hold on. Jeez, oh man. 680.5b says, where required in this article, ground fault protection of receptacles and outlets on branch circuits rated 150 volts or less to ground and 60 amps or less shall be provided with a Class A GFCI. No, I'm good with that. That's a Class A. Okay, so that's your GFCI. Now, C is above 150 volts. All right, that's perfect. Where
yeah, we showed. So it's kind of the flow chart.
Yeah. So when I first read this one, I thought it said a special purpose, but it's a Class A, and a Class A is 150 volts or less to ground and 60 amps or less. And now A tells us that it's unless otherwise noted or in addition to the requirements in 210.8. Now, C says, where required in this article, ground fault protection of receptacles and outlets on branch circuits operating at voltages above 150 volts to ground, not exceeding 480, single phase or three phase shall be provided with a special purpose GFCI protection not to exceed 20 milliamps. There's that 20 milliamp number that you had noticed. And they reference 943C outline investigation. So, and then 680.6 tells us that all of the equipment in these swimming pool areas have to be listed. So you got to have a special purpose GFCI listed to 943C.
Yeah, I don't see a problem in the language, Tom, but I guess probably just you confused. I guess the less than 150. Yeah. One quick thing, I guess Tom mentioned that we were going to share, but I guess we're under time pressure here. Class B. Class B doesn't exist. And
Yeah.
the reason is Class B is obsolete because, I mean, think A, C, D, and E. Where's B? Anyone would think, where's B? So B is obsolete because it was the class that was installed in the light fixtures of swimming pools up until the 1968 NEC version. And up from that point forward, Class B became obsolete. And I believe, I mean, I wasn't there, obviously, with the history, but I know that from my understanding, Class C, D, and E are based off the Class B requirement. The Class B back in the day had 20 milliamp trip level. So I think the 20 milliamp trip level was kind of inherited from Class B Gfcis that, like I said, they're obsolete, but they used to be installed to protect light fixtures for swimming pools. And, you know, now it's 2022, almost 2023. We're going back to protecting swimming pools using Class C, D, and E. So I guess if you think of it, it's kind of more like something we did back in the day. Now we're kind of, after all those years, we're going back to something that was done before. So
Right.
I find it interesting.
Yep. And then in 680.22 for lighting receptacles, because remember that text in 680.5 said where Gfci is required in 680, right? So if you keep following polls and you look at 680.22 for lighting receptacles and equipment, it'll say in 680.22 ground fault circuit interrupter and special purpose GFCIs protection, all receptacles rated 125 volts through 250 volts, 60 amps or less, have to have GFCI protection complying with 680.5 or special purpose GFCIs protection complying with 680.5C as applicable. Well, that's 125 volts through 250 volts, so you can't use a special purpose there, right? Because special purpose is above 250. So that's where I think the language in 680.22 was a problem. And then in B, luminaires in 4, now this is more generic. It says luminaires, lighting outlets, ceiling suspended paddle fans installed in the area extending between 5 foot and 10 foot horizontally from the inside walls of a pool shall have GFCI protection or special purpose as applicable. And that would be the as applicable would be the voltage levels, right?
Right.
So
and Tom, I want to remind everyone that this is the first time ever for special purpose. I mean, not ever. That's a different story. But let's in this section that special purpose GFCI has made it to the protection of swimming pools 680. And like you always say, Tom, it's if anyone thinks the language needs to be improved or there's something that could be done better, it's always an opportunity for improvement. And look forward to your public input in the 2026 cycle, right?
Yeah, and then so here's another. Yep, it's another example. 680.32. It says ground fault circuit interrupter and special purpose. All electrical equipment, including power supply cords used with storable pools, shall have GFCI protection complying with 680.5B or 680.5C special purpose as applicable. So that would be the any voltages. And then in the second paragraph, it addresses the GFCI protection. So I guess the only area I see, because somebody brought this up to me, that there's some confusion with the language. And I think the only problem with some of this language is where it says, for example, all receptacles rated 125 through 250, 60 amps or less shall be afforded GFCI or a special purpose GFCI. Well, you couldn't put a special purpose GFCI on those receptacles because special purpose is above 250. So I think that the language could be used, can be cleaned up a little bit, but I don't think that it's a problem.
I mean, you can get a Class C that is like less than 150 volts, like I mentioned in the chart. But just remember, you were not trying to replace Class A with special purpose GFCIs. Class A is your go-to until you get to an application, like a point to an application that you can use Class A. Then you start considering Class C, D, and E. So I guess the point is that what Tom and I would like to emphasize, those new classes are not to replace Class A. They're not better.
Right.
It's just a complement. Now we have a family of classes. Use Class A. In those cases that you couldn't use Class A because, let's say, the voltage was higher than the Class A available commercial products available, or the Class A the leakage current in your system was just too high, because you can have a case that you can install a Class A and it keeps tripping all the time because of the inherited, the leakage current, the charging capacitance is too high in your system and just trips. So in this case, it's gonna maybe think of migrating or utilizing Class C in lieu of Class A because of the higher leakage current. But in those applications that Class A is required by the code and they're designed for, you shouldn't use special purpose GFCIs. That's the bottom line. Is they're only used when Class A is not applicable. So it's a complementary, not
it's substitution.
Yeah, right, for sure. And Don Ganir has a good question. I don't know if you saw this, Tom.
I did.
Said, is it likely that special purpose GFCIs trip quicker than maximum permitted trip time like GFCIs? And I'll say absolutely. The equation that the equation that we showed here, Tom and I, and this on one of the figures, is the maximum, the absolute maximum trip time allowed by UL. Manufacturers would trip quicker than this time. So, like for example, the easiest data point is 20 milliamp is 1 second. So according to the UL equation, 20 milliamp leakage current requires maximum trip time of 1 millisecond. Of 1 second. 20 milliamp is 1 second trip time. So for a commercial product, there's no way that any manufacturer will push it to 1 second. So you could trip at, let's say, 0.5 second or 0.8 seconds or maybe 0.2, depending on the design. So this is kind of manufacturer thing. But like you said, Don, you would absolutely have to quick faster than the required equation. And the reason is simple. When we do testing, you have to abuse the product. You kind of go through a temperature chamber, humidity. It's tested from -40 up to 60 degrees Celsius. Which is 120, I think, Fahrenheit. -40 is the same on both scales, Fahrenheit and Celsius. So you can't just push and when things get really hot and really cold, it kind of slows down and just does funny things to the electronics. So if you're designing your product to trip at 1 second exactly on the dot, it's just not going to work. So you need to be quicker, just to give yourself the cushion, like some kind of like a leeway when things kind of go not as designed because of temperature, humidity, and all other factors.
Yeah. So to answer Lou's question, and Dawn, thanks for saying that. When I was reading the code changes, when I was reading some of the text in 680.5 A, B, and C, and elsewhere in 680, like 680.22, and anywhere that they have GFCI protection or special purpose, that's in the 2023 code. So the stuff that we're talking about right now is not in the 2020 code. It is in the 2023 code coming down the pike, and it will be a part of, and you'll learn more about this in the where's it at? Hold on. In the IAEI's changes, analysis of changes, which you can pre-order right now. So the analysis of changes will include the specific areas within Article 680 that now require the use of a special purpose GFCI, which is the stimulus for this discussion, because when the National Electrical Code starts to require a technology that is new, I wouldn't say it's new, Nehad, right? I mean, the special purpose has been around, but it will be new for the NEC. And so it's important for us as electrical professionals who have to follow the National Electrical Code, and in areas where you might want to exceed the National Electrical Code, understand the technologies that are out there and the correct way for proper use and whatnot. So I know that we've covered, so Nehad, we have covered, we went through what the difference is between a GFCI and a special purpose GFCI. We talked about the two different thresholds. We talked about the concept of let go versus defibrillation. We spoke to the clearing times. We showed those curves. We talked about one of the important installation aspects of the special purpose, which is that equipment grounding conductor. And so we went through, I think, and then we even touched on where in the National Electrical Code for the 2023 where they can find it. So hopefully, I don't know that we missed anything. Can you think of anything that we missed before we close?
I think we did good for an hour and 9 minutes. So I think we did pretty well. Don Grenier just had an interesting question. I guess, Don, thank you, because Don keeps asking questions that are very, very, very important, and it kind of helps with the I guess, enrich the discussion. So thank you, Don. To answer your question, so Don's question is, will the wiring requirements change where Class C devices are installed to monitor the equipment grounding connection to the equipment? And like Don identified, so now we need to monitor the equipment, the grounding, the equipment grounding conductor of an equipment. So the change in the wiring is, I guess, I'm not going to talk commercial, but the technology that exists on commercially today, maybe in the future there'll be something better. But as of now, the way to monitor the equipment grounding conductor is to run a separate circuit, like it's called a pilot wire. And so you have a wire that is run from your device, let's say the source, because the device is usually installed at the source, like in a panel or something, like a breaker. So it's not a breaker, but it's similar to a breaker. So installed a pilot wire that runs from the unit, the Class C, Class D Gfci, special purpose Gfci, and it goes all the way to the equipment. And there's what they call a termination. So it's terminated by a Zener diode, and this is how the equipment grounding conductor is monitored. So yes, there will be a little bit of a change. You'd have to run a pilot wire. A pilot wire is a 16 gauge, 18 gauge, just a very it's not like a big conductor or anything, like a small wire that just carries a DC signal, a very low DC signal that the device will send all the way to on the pilot wire to the Zener diode termination for some technical reason to ground back. And as long as the device can monitor, can see the signal coming back, in the circuit, then you know that the equipment grounding conductor or your grounding connection is still solid. Once the signal is lost, then the device will detect that, there's something wrong with my grounding, so I just need to trip.
Yep. Excellent. Namaste Yi from India. So thank you for joining us. So we had India. We've had we've been truly, we have been truly international on this call. So I appreciate everybody dialing in. And Fred, thank you for dialing in. Michael Hofkin, thanks for being here. Steve Terry, Robert from Omaha, Don Ganir, always a value to have him on the line. Steve Terry, thank you very much. Mervin, thanks for joining in, and everybody else that's out there. So we really appreciate you dialogue. Thank you, Nehad, for joining in, and thank you for joining in last week also. So this is Nehad twice in a row. So everybody's going to know you. So thanks again for what you do for the electrical industry and electrical safety. I know you're out there a lot.
Everything you do, and you're just taking the time and having those presentations and taking time out of your busy schedule. So I guess the whole industry, including myself, appreciates what you do, Tom. So thank you so much.
Well, thank you so much.
To coming back to be another guest, not next week, because it'll be like 3 weeks in a row. Be too
yeah,
much.
No, that would be too much, Nehad, for 3 weeks for 1 month.
Yeah, for sure. I'm not planning to be here. It's not that I don't want to, but I think it's just too much to handle me 3 weeks in a row.
Excellent. And Michael Hofkin says, don't forget to like and share this broadcast with all of those out there. So please don't forget that. And Jody Wages found his special purpose. So thank you for tuning in as well. And Robert Zweifel, thank you for joining in. So
Robert is a good friend of mine as well. Thank you for tuning in, Robert. And I hope to see you soon sometime. And
excellent. Just
don't forget, guys, if you want to dislike this video, just do it twice. You press the like, dislike twice, 4 times, just like an even number. If you dislike this video, just
if you're gonna hit the thumbs down, you have to hit it twice. If you're gonna hit the thumbs up, you only got to hit it once. Don't forget to subscribe to the YouTube channel. So if you're watching this on LinkedIn or Facebook or wherever anybody else has shared it to, please get out there to the IAEI's YouTube site and subscribe. It's free. And look at the valuable information that you get. So, and there will be much, much more. All right, Nehad, we got to sign off, brother.
Sure. Thank you, Tom. Thanks, everyone, and have a great day. Hopefully this was a good hour that you spent, I guess an hour and 15 minutes that you spent with Tom and I.
Thanks for spending time. Thank you. And everybody out there, thanks for what you do for the industry. Thanks for what you do for electrical safety. And remember to stay safe and please stay
healthy.
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 Yep. All right. Take care, Willie. See ya.